We will wait for a few more minutes before it's done. Seems like all our international students disappear, except I'm down here. Is it? Maybe they will come later. Um, so, um, so I put out some definitions here. Sometimes it's important that you know whether zero vector is allowed inside the definition or not, or certain theorem. Okay, for example, this orthogonal set here, we said that a set of vectors is orthogonal. Okay, if each pair of distinct vectors here from the set is orthogonal, so you need to check for every pair their dot product is 0. So in this case here, there's no restriction whether you can or cannot take the zero vector. Okay, so obviously zero vector should be orthogonal to every vector, right? Because you always get 0 if you take the dot product. But if you notice that the next theorem follow is if you have a set of orthogonal set of non-zero vector. So in this theorem here, you only consider orthogonal set of non-zero vector. Then X is linearly independent. Okay, because we know that zero vector is always linearly dependent, okay, to the other vector. Okay, so that's why we need to throw away the zero vector in this theorem here. Okay, the other example is eigenvector, eigenvalue. Okay, so we say that a lambda is a eigenvalue of A if there is a non-trivial solution, okay, X such that X equals to lambda X. So in this case here, if you want to check whether a scalar satisfies eigenvalue condition, you need to find a non-zero solution, okay? Because last time we see that if you take a matrix, you times 0, always get 0. And that 0 will satisfy any scalar times 0 to be 0. Okay, so it's not well defined. Okay, if you include 0 as a eigen. But if you look at the definition of diagonalizable matrix, okay, so what does it mean? If you can write it as PD P inverse, okay, for some invertible matrix P. So in this case here, actually your A could be zero matrix. Okay, it could be zero matrix. Why? What's the eigenvalue for a zero matrix? Huh? 0. Okay, with multiplicity, what? What's the multiplicity? Depend on the size of your zero matrix, correct? No? If you take zero matrix minus lambda I, what do you get? Get minus lambda on the diagonal. Okay, yeah. And then what are the eigenvector? Actually, is the you can take it as a you can take it as anything basically, but you can take it as a standard basis. Correct. So if I'm gonna write this thing out, right, it's like the zero vector equals to zero matrix equals to identity time zero matrix time identity inverse, which is identity. Okay. I is invertible. Identity matrix. Okay. Access. Question. Question. Okay, so since this is the last week, right? So maybe we do some concept check here. So what is actually linear algebra? You already learned for 4 weeks here. What does it mean by linear algebra? Anyone have any idea? Now, what is linear algebra? I have no idea. I think there's a very good translation from Chinese. What's the Chinese name for this course? Oh shit, forgot how to write that. Okay. Okay. So in Chinese, very clear, right? Xian. What is xian? Line. Did you see line here? Linear. Okay. So this course is about line. We study line. Okay, correct or not? We study line or not? Because we look at vectors, right? The line vectors, and then we look at their span, right? We look at the span of them. Okay, and then we see how these lines get changed, right or not? So linear transformation. So we send lines to line transformation, correct or not? We send line to line how? Tx plus y equals to tx plus ty, correct? Okay, we send scalar multiple of line to scalar multiple of line. Okay, so basically we just send line to line. Okay, so we are studying function on lines. Okay, linear algebra. Okay, no. But until this chapter 6, right? So if you have a line, right, you put it on maybe a table. What's the obvious thing you observe here? What's the obvious thing you observe here? You have a line, okay, put on the surface or the other line. What can you observe here? Two of them will form something called the angle. Okay, so angle is another thing to capture how these lines react with each other. You know, angles and also the length. You know, the length, yeah, length. Okay, so out of these line here, we will know angle and length. These two quantity here. Okay, let me write down length and angle. Okay. And then we'll link this idea back to span and linear independent also. You know, does it make sense? Okay, so actually this morning, I upload two link for you, two website. But, so if you go to the week 4 of our Moodle, sorry, week 4 or week 5 now, week 5 already. But, yeah, so I upload two links for you. So if you are Chinese speaking, right, or you know Chinese, you can go and follow this YouTuber. Okay, he explained linear algebra in a very geometrical way, and then explain it from a very simple concept. Okay, you can read through You see? You know your pen, so you can read what's the concept of linear algebra. And if you are an English speaker, right, there's also very good English channel, Three Blue One Brown, explain the maths in very good concept, very very good examples. Yeah, and not skip.
What do you think is my peer manager asked me, oh, so which company are you going? I said, no, I'm not going anywhere.
Yeah, there's a series on linear algebra also. Yeah, very simple. Okay, so these two YouTubers are doing very good job. Yeah, you can watch them. Okay, no. Yeah, these two are very good explaining maths again. Okay. Yeah, if there's any concept you don't understand, you are still confused, you can go through. Okay, any question? Any question before we start new lecture? Do you have question from last week? Or you have the question for this week quiz? So this week's quiz is on chapter 5 and 6. Hopefully we can finish it by Wednesday so that we can have quiz on Friday. Okay. I think follow my project, when I can finish this course, I guess. I think on Friday, maybe I'm planning we could take quiz in the second hour. Okay, we could take quiz. So I haven't confirmed yet. Let me teach first and then see how it goes. Then I'll discuss with the other lecturer. Maybe we'll take quiz in the second hour. And then after quiz, you can choose to leave or not to leave. And then we will do some summary. And then maybe I give you some tips on exam. And then you can ask question, you can discuss question from a tutorial, from a textbook that I never do before, that you want to know, we can do it together. Is it okay or not with this thing? We take this thing. Yeah. Okay. Yeah. But I haven't confirmed yet. Let me teach this 2 days first and see how it goes. Yeah, and then we confirm. But quiz content is chapter 5 and 6. Hopefully we can finish by Wednesday. Okay. So let's see how it goes today. Right. So let's do some recap. Yeah, let's do some recap here. So last week, we defined what's called inner product. So basically, what's the inner product is? It's a map. It's a map from Rn to Rn. Sorry, taking two Rn, and then give you a piece of real number here. Okay, so you take U, V, and you dot them together. So anyone remember what's the formula here? How you multiply n by 1 matrix together? Oh, what's the formula here? What's the formula here? Okay, there's another way to talk about this. U transpose T times V. So this is a matrix way to talk about it. So you basically you make it into a 1 by n matrix and then multiply by a n by 1 matrix. So you get a number. Okay? Or like Yi Yang, is it Yi Yang? Yeah, like what Yi Yang says, if you write down your vector in terms of n numbers here, n copy of numbers here. So what do? You just take the multiplication of a real number in the corresponding spot. like this, and then add them up together. Okay, so it's very important that you learn this transpose formula here, because later we're gonna see it again. Okay, so basically you turn the other vector around so that you can do matrix multiplication between two vectors. So if I want to write it out in vector form, it's like this matrix form, I mean. Okay, row times columns. Basically, you have a row times a column. Okay. Okay, so this is about inner product. After inner product, inner product don't have these two lines, right? So it's just basically a dot. So dot here. Dot between two things. And then we have a modulus, norm or length, or we call this norm or length. And so what does this do? You feed it a vector, it gives you a number. Okay, so how will we define this? So we take a vector u, and then it split out what? Basically, you just dot it with yourself, and then you take the square root. Okay. So anyone recall you learned something called modulus or absolute value, maybe from your high school. All right. So this is a modulus function on what? If give you an r, split out an r. So how do we define this? Do you still remember? So yeah, if I take a number, it becomes modulus x. So what's modulus x here? Sorry, give you a positive number. Okay, so I give you x if x is already positive or 0. It give you negative x if x is negative. So I put it into positive. But you see that the norm is a generalization of this guy here. So if you take n equal to 1, right? Okay, so what do you do here? X times x and then square root. So that's why you always get positive here. Okay, so norm is a generalization of the absolute value that we know, or the modulus. Okay, so if you think of it a geometrical way, right? So you have a line, and then you have a line 0 here. You have a 0 point here. And then where is your x? There's few way you can place your x. Either x is on the right hand side of the 0, or it is on the left hand side of the 0, or it is 0 itself. Okay, but modulus x is really just the distance from 0. Okay, the distance from 0. Distance cannot be negative, right? For example, Southern, where's your hometown? Huh? Kedah. So from Sepang to Kedah, how far? 4 hours. In terms of times, okay, in terms of time, it's 4 hours. You know km how long? No. 4 hours, I think about 400 km. I don't know if your speed is like 100 km per hour. 400 km. Then, if your distance from Sepang to Kedah is 400 km, so what is the distance from Kedah to Sepang? Also 400, right? Cannot be negative 400, right? Okay, so I mean, it's normal that we define length to be a positive number. Okay, no matter which direction you go. So that's why vector has a interesting property here. It doesn't only have length, it also have direction. Okay, so we can remember which direction we go. Okay, with vector. So let me see here. Yeah. So if we define this, actually we have a theorem, right? We know that u dot v is actually equals to the length of u times length of v cos theta. Okay, so actually the dot product we define, right, between two vectors gave you this three quantity here, combine. And we have U, we have V, and then there's an angle. Okay. Yeah, so far, okay. So good. Okay. Okay, so the last thing we do is about orthogonal projection. So let's recall what orthogonal projection is. So the definition is the orthogonal projection of y onto u is given by the following. Given by approach of y onto u by y dot u over u dot u times u. Okay, so how do we think about this orthogonal projection here? So basically, if you're gonna start this orthogonal projection procedure, right, you need two vectors to start with. Okay, you need two vectors to start with. So let's borrow these two vectors here. So let's borrow these two vectors. So in this case, we call it u and y, right? So let's make it u and y. U and y, u and y, and u here. And let's call it u and y here. So basically, what does this do here is we split y into two components here. I mean, we call it a horizontal component and a vertical component. Okay, horizontal and vertical. So let's call it y hat, horizontal part, and vertical part, we call it z. Okay, so where's the orthogonality here? Where's the orthogonality here? Where's the orthogonality? Okay, wait, before that, do you still remember what orthogonal means? Okay, so let's recall first. Let's recall what is orthogonal first. So, two vectors u dot v are orthogonal. Orthogonal if what? What's the definition? What's the definition? Sorry? 90-degree. I think before that, before the 90-degree, what's the definition? 90-degree should be a consequence of this definition. Well, I mean, perpendicular and 90 degrees is the same. What's the definition? Yes, the dot product equals to 0. Okay, so why from here we know that the angle is 90? Because go back to this theorem here. If you want this dot product to be 0, what happened? These two, if these two are non-zero vector, right? Usually we look at non-zero vector. Then their length should be non-zero. So what's the only way to make this product to be 0? Cos theta must be 0. So when is cos theta 0? 90-degree. Okay. Yeah, so they are perpendicular. So where's the orthogonality in this picture here? It is between z and y hat here. Okay, so that's why we call it a orthogonal projection. Okay. Okay. So this y hat. So this y hat here actually is this projection. Okay, last time I derived it for you, right? Okay, I derived it for you. So you can see that this horizontal part here is not the whole u. is not I mean it's almost always not a dot u. Okay, it's just a scalar multiple of this u. Okay, so how long you need to take? What's the scalar you need to take here? Okay, it's based on this ratio of this two dot product here. Okay, so I think this is easy to remember. This formula is easy to remember. How to remember? How to remember? Huh? So you're gonna project, if you're gonna project your y to your u, you simply take y dot u. Okay, you take y dot u, and then you divide by the length of u squared, and then this is the scalar you need. Does it make sense? Okay, so if you know y, you know y hat. Can you find z or not? How? If you know y, you know y hat. Do you know z? How to find z? Huh? Sure. So how to find z? If you know y, you know y hat. How to find z? This is a triangle, right? Equals to y minus y hat. Is it correct or not? So minus y hat. Okay, so let's follow this. So last time when I mean, how do we decide whether two vectors are the same? The starting point and the ending point is the same, right? Okay, so you can see that z go from bottom to the top, right? So where does this vector here start? Okay, you start with, okay, maybe it's not a good way to write negative y here. So like this. Okay, so we're adding two vectors together. One of them is a negative of y hat. So y hat is this vector here. Negative y hat means what? You turn the arrow to the other side. Okay, so if you start from bottom, you go to the left, and then you follow y. Okay, it's the same place. Does it make sense? Okay. Yeah. So I mean, this interpretation is very important. It's not like a I mean, number actually is also important, but in number is also important. But this negative on vector here is really turning the vector in the other direction. Okay. Yeah. How to say this? Maybe in number, right? Maybe you say 4 minus 2 is 2. But what is minus 2 means? You take away 2. Okay, maybe you learn it as a taking away 2. Okay. But the other way to think about it is negative plus 2 is always 0. So negative number is the number that when you add to the positive counterpart, you get back to 0. Okay. Yeah. This is what we call inverse, the idea of inverse. Okay. It's okay. All right. So let's try an example here. Okay, let's try an example here. So let's take this two vector. Okay. Hello. How about I let you try this first? Let you try this question. Maybe I give you 2 minutes. Okay. So how do you do this question? So you can do this question conceptually. So if you pick y and u, so what's your y and u? So 7, 6 is on the first quadrant here. 7, 6. And then negative 2, 4 is in the second quadrant. Be something like this. Okay, so you're trying to project. Hey, hello. Well, hello, testing. Okay. Thank you. All right. So let's come back. So before we do this example, I want to teach you a way to read question. I want to teach you a way to read question. So even before we reading what we want to do, right? Okay, we should know what first sentence is saying. Okay, so when they say the first sentence, you should have this picture inside your mind already. Okay, so 7, 6. Yeah, and negative 4. Over here. So this is U. This is Y. Okay. And then only you continue and read this sentence. Okay, you continue and read this sentence. Now we're gonna write Y as two vectors, sum of two vectors, where Y1 is in the span of U. Okay. So meaning what? Y1 should be on the same line of U here. Okay. And then Y2 is orthogonal to U. So you should imagine a picture like this. Orthogonal. So orthogonal way. So somewhere around. Okay. Going this way. Yeah. So you're gonna decide what's the scalar you need to take on y here. So I mean, let's create some terminology here. So maybe we call y1 as a horizontal. Should we call it? Okay, never mind. Don't want to create this new terminology here. Okay, so we're gonna write y here as a sum of y1. Yeah, let's draw it here. y1 and y2. Okay, so our job is to find this y1 and y2. Okay, okay. So I don't want you to like, although not like, okay, there's one way, I mean, our student like to do, or maybe even me also like to do before, when I was a student before. We typically don't read this. We only go for the last sentence. We catch the keyword, orthogonal, sum. Then we straight away use formula. Okay, so this is not a very good way to do exercises because this is not understanding. Okay, so it's just catch some keyword and then you think that, oh, this is what I need to do, and then just do it. Does that make sense? Okay, so to understand what question asking or understand knowledge or listen to people, you always have to know what's the what is it? The prerequisite first. Okay, the condition, the precondition you need to know first. Only then you can start doing. Because why? You know why? You know why this is important? Because if they give you rubbish in the first sentence, you don't need to do second sentence already. Does it make sense? Because nowadays people do it differently. Even if you give them rubbish, they still can compute some rubbish for you also. You understand? So make sure that they don't give you rubbish at first. Okay, if they give you rubbish, you say no need to continue anymore. Okay, because it's rubbish. Okay. Okay, so let's use the theorem that we said just now. Right, so this fit into the orthogonal projection condition, right? So to find y1, so what is y1 here? It's actually projecting your y onto u. Okay, so what's this formula here? Basically, you do y dot u over u dot u times u. Okay, so this will tell you what's the scaling you need for your y1. Okay, so this will tell you what's the scaling. So basically, you need to write your y1 as alpha times psi u here, where this alpha is y dot u. Y is equals to y dot u over u dot u. Okay. Can memorize this scalar now? If you're gonna project to that u, you just take your vector and adopt that u. There's only two things you need to take. And then remember, divide by the length of u. Okay, so what's this quantity here? Anyone computed? Anyone computer, what is it? What do you get? Huh? Anyone? What's the number you get? Sorry? Negative 1 over 2. Negative 1 over 2? Got negative? Anyone else got negative? Just 1 over 2. Should be just 1 over 2. Yeah, okay, should be just 1 over 2. No negative. Okay, so you see, I mean, to see whether your calculation makes sense or not, right? See where does this vector lie? Negative 1, 2. Also lie on the second quadrant. If let's say if you computed negative 1 over 2, what do you get? You get 2 and minus 4. So it's not on the span of u anymore. Okay, this is one way to check your calculation. Does it make sense? Okay, yeah. So if you calculate something wrong, it won't be the span of u anymore. Okay, so this is y1. So in this case here, can you find y2 or not? How do you find y2? Solve them.
The negative
Uh,
negative y1 plus
y.
y.
Good. Okay, so you take y plus negative y1. Because we know y, and then we just computed y1. Okay, in this case here is 8 and 4. So leave on, okay, 8 and 4 here. Okay, so what else you can check here, whether you know something is correct or wrong here. So there's one checking maybe you can make here is, you can check whether your y2 dot your y1 is 0 or not. Okay, because you want them to be orthogonal, right? Because you want that y2 is orthogonal to u, so you orthogonal to every scalar multiple of u. Okay, so in this case here, you can see that 8, 4 dot with -4, -2, 4 equals to 1. -16 plus 16 equals to 0. Okay. In your quiz, some of you, you computed the solution, right? And then you do check. You say checking is correct, but your calculation is wrong. So are you really doing the checking or not? You just give me like this. Okay, you just give me like this. X4 dot -2, 4 equals 0. There's no this intermediate step. And then it turns out that your calculation also wrong. So what checking you are doing? 不要自己骗自己啊 please. 不要自己骗自己 okay? It's better you don't write the check if like that. 好过不要做，是不是？ Right. So if you are checking, please do a real check, okay? Otherwise, you lose the meaning of checking. Clear or not? You cannot say, oh, I compute, and then write this check. For what? 不懂哎，什么 mindset 啊？我是不理解啊。对吗？ If you want to check, then do a proper check, and then you will see that, oh, let's say, if you have a calculation error here, so you will see that, oh, -24 plus 16 is not 0. And then you get what? -8, non-zero. So go back and check where's your calculation go also. Okay, it's not writing for the sake of writing. Please, 不要自己骗自己, okay? Okay. Right. Next. Okay, so far, okay or not? This example. Okay, next. A set of vector is an orthonormal set. Okay, it's an orthonormal set. If it is an orthogonal set of unit vectors. So there are two things here, 1 and 2. Okay, so orthonormal set here, we also combine two words here, orthogonal and normal. Okay, whenever we say a vector has a length 1, usually we say it is normalized. When we say normalize a vector, okay, so maybe let's define another word. We say that a vector is normalized. So let's call our vector V. Okay, V if V has length 1. It has length 1. So orthonormal means your set of vectors is orthogonal. Okay, and also all of them have length 1. Okay, let's do this check and then we will have a break. So let's do this check here. Show that V1, V2, V3 is an orthonormal basis of R3. Yeah, so it's an orthonormal basis. So how many things to check? Before looking at this, orthonormal basis, how many things to check here? 2 things. Okay, so what are 2 things? Amber, try first. Never mind, wrong also never mind. Dot product equals 0 because you're gonna check orthogonality, right? So one thing is orthogonality. Okay, so you need to check the dot product is 0. So how many of them? Not even knowing what are them first, we already know that there are 3 vectors, right? So we know that how many things we need to check here. I think there are 3, right? V1 dot V2, V2 dot V3, and then V1 dot V3 have to be 0. Okay, and then what else? Unit vector, so you need to check whether they are unit vector. So normality, let's call it. Yeah, so you need to check whether V1, V2, V3 are length 1. Okay, but this one is just orthonormal, right? We still need to check whether it form a basis or not. Okay, what else you need to check for basis? Sorry? Span and linearly independent. Okay, so third thing we need to check basis. Basis here have span and linearly independent. Okay, obviously you can go through the definition. Okay, well, definition is what? For every B in Rn, you need to write down the what? You need to find C1, C2, C3 such that you can write it as a linear combination. And then linearly independent, you need to solve for the homogeneous linear system so that it has a trivial solution. But here we got easy way to deal with these two things. We got easier way to deal. Using the theorem, we know. For example, orthogonality have connection to which one of them? I think both of them. Okay, one of them. Let's say, what's the relation between orthogonality and independent? Okay, so if you have an orthogonal set of non-zero vector, it implies that implies what? Implies that they are linearly independent. Okay, this is a theorem we know. But we know that the dimension of R3 is 3. We already have 3 linearly independent vector. So it will imply span, okay, by the basis theorem. Since we know that dimension of R3 is 3. Okay. Okay, no. Yeah. Do you still remember why dimension of R3 is 3? There's an easy basis you should remember. Huh? Sorry? R3, why dimension of R3 is 3? So what's the easiest basis you should know? 1 0 0 0 1 0 0 0 1. What are they called? Standard basis. Okay, standard basis. Okay, so for standard basis, right, you should know how to show span and linear independent. Very easy, right? Okay, the REF form is already 1 1 1 on the every column. And then span is also easy to see also. X times 1 0 0 plus Y times 0 1 0 plus Z times 0 0 1. Okay, so this is the easiest basis. Okay, so we should check these 3 things here. Okay. Do we check it? Okay, I let you check. Check now. Let's take a break. Let's take a break. Take a break until 11. Okay, let's take attendance of Jiawei here, no? Du Jiawei. Du Jiawei. Okay. Yeah, Han? Toilet, okay. Yanshen. Jiaming. Jiaming just come on. Su Han. Okay. Zhen Jie. Zhen Jie, where's your friend? 他没来，他去哪？不知道。天天，天天呢？天天为什么越坐越后面了？啊？哦，迟到哈，OK。 越好。OK，先高分分担年幼年幼，where's 年幼？年幼 not here。宏伟，OK，报名就以令思雨not here。Bryson here。福顺 K 福顺，OK。郑瑶 here。秋子芳龄林夕子珍，好的。林心宇心仪后面的，你沟通刷鱼机，陶子瑜吴生瑜任若琪李昌瑞卢浩奇，好的，OK。洪泽洪泽，或者叫赵洪泽，高紫金呢？OK。陈军，OK。Amber here，有丁 here。吴彦Abdurrahman here，OK。思成 here。白嘉宁这边，嘉怡岳阳张岳阳，OK。吴俊相俊豪后面雷乱立坤有的逸轩萧亚轩老师 Ivy the whole game disappear。百物城葛文业与黄健孙波东，OK。钟义阳张汉慈有没有？OK，这个陈泰利高子昭对对金思豪，OK。李云林昌旭，OK。刘涛呢？圆前面是不是？年幼累啊，年幼。邓瑞阳，洪明在前面是不是？浩瀚吴一格，一格好像看到有一格有在那个。徐泽瑞、于子洲、赵泽宇、Iba 没有 Benny not here。Nuri、Senai also not here。李轩、冲之气，Edward here。他指挥呢？他指挥有没有？Mark 一间，Nicole 子君、初辉月、罗星东、Salami, I think I see Salami, right? Salami sleeping. Lunichi, yeah, okay. For this class seems there's a lot of SWE. SWE, in particular 2409, very big batch. Uh, 2409 batch, do you guys know each other, SWE? You guys know each other? Don't know? Okay. Don't know each other. How big is your class now, SWE? 80, 90, 90, 90. Total number, SWE. 202409. 170? Wow. I think 3 years ago, I teach SW is just about 60. Almost triple. I see. Oh, no wonder 2409 so many students here. Then your class is usually in the lecture hall. And then you guys split into tutorials or not? Seldom? Then how? Depends. How about the discrete map?
Split.
So you have tutorial. Or you guys, SW have 3 groups?
No, for discrete.
Uh-huh.
Maybe 3 groups.
What are the 3 groups?
Chinese, for Chinese
And
students, and then international, other international
Oh.
students.
Is it?
And local.
Okay. Oh, wait, let me think. I thought discrete math is taken together with AIT and BMT. So you guys combine with BMT.
Yes.
Okay, I think let's start first. Okay, so given this 3 vector here, let's check whether they're orthogonal or not. Maybe we just do it together, very simple check here. So v1 dot v2, so what do we get here? 3 over square root 11 dot. I think almost you can use inspection to see the answer, because you can see that the denominator is always the same. Okay, it's always the same no matter how you multiply. So you don't actually need to multiply it out. So the main point here is the numerator. And the main point here is numerator, yeah. So 3 times minus 1 is minus 3. Plus 2 plus 1 is 0. Okay, so you get 0. And how about v2 dot v3 here? Can we straight away compute? So numerator, you see, denominator are all the same, right? All are square root 6 times square root 66. So you need to care about numerator, okay? So first you get -1 times -1. Second, you get 2 times -4. And then third, you get 1 times 7. Denominator is the same. Square root 6 times square root 66. So 1 plus -8 plus 7 should be 0. Okay. And then let's move these away. Then how about v1 dot v3? Okay, so what do you get? 3 times -1 plus 1 times -4 plus 1 times 7 over square root 11 times 6. So -3 plus -4, -7, -7 plus 7, you get 0 again. And then you check normality. Okay, so that's why there's a weird denominator dividing here. So we will check that their length is actually 1. Okay, can you quickly see by inspection? Why is it 1? Why they divide by this square root here? Can you quickly see the calculation? Okay, so let's check. So for example, what is the length of V? It's actually square root V1 dot V1. And then what is V1 here? So V1 dot V1 is what? What is V1? 3 over square root 11. 1 over square root 11. Take 1 over square root 11. Okay, you do dot with itself. And then you take square root. Okay, so what happens here? You have 3 over square root 11 squared plus 1 over square root 11 squared plus 1 over square root 11 squared. Okay, so if you want this to be 1, right, what should you hope for? What should you hope for? You should hope that your numerator equals to your denominator. Can you see that? What is your denominator is 11. Okay, so you need to hope that your numerator add to 11. So 9 plus 1 plus 1 is 11. Okay, so you have square root 11 over 11, which is 1. Okay, no? Yeah, so that's why your so there's one, misconception here. People usually will think that is enough to divide by 11. Okay, they are dot product, but actually it's not. Why? Because when you compute this inner product here, right, you're gonna multiply your denominator twice. Okay, so if you just put 11 there, you won't get the length division here by 11. Instead, you'll get 131. So you won't get to the length 1. You are dividing by more number here. Okay, so make sure that you divide by the right length. Okay? It's not length square because usually students will confuse one. They will confuse one. So here, let me warn you. Warning. Okay, the length of V is not V1 dot V1. Okay, usually students easily forget this square root 1. Does it make sense? Okay, please don't forget this square root. 不要忘记这个开根号。Okay, yeah, because you need to remember that in this calculation here, you're gonna multiply your denominator twice. Okay? You're gonna multiply your denominator twice. If you forget the square root, then you will have big problem. Okay, so can we quickly check on this two here? Okay, so 1 square plus 2 square plus 1 square is it 6? 4 plus 1 plus 1 is 6. Okay, square root 6 times square root 6 is 6. The other one, 1 squared plus 4 squared plus 7 squared. 49 plus 8. No, sorry. 49 plus 16. 65. 65 plus 1 squared. 66. Okay. The other you left as homework. And then, so basis will follow easily. Okay, so because we check that the 3 vectors are orthogonal, so they are linearly independent. And then we know that R3 is dimension 3. So that's it. Okay. So the third part here come for free. Okay, come for free. Okay, because we know that V1, V2, V3 is orthogonal. And we know that dimension of R3 is 3. Okay, come for free. Okay, basis part come for free. Yeah. Okay. So there's a very interesting interesting observation here. So let's try this observation. It's interesting observation here. Okay. So if we're gonna take this our V1, V2, V3 here. So let's take. Okay, and then I form a matrix. Let's form a matrix using this V1, V2, V3. Okay, and then I compose, copy, paste here. Okay, if I compose them, one of them I transpose it. Okay, we transpose it. And then here, what do we get here? What do we get here? The magic here is this is an identity matrix. You believe or not? Identity matrix. Do you believe? You believe or not? Okay, so let me write down easier term. Okay, do you want to verify or you believe me? You believe me or you want to verify yourself first? You want to verify first or not? I'll let you verify first. Later, I'll tell you why it is always true. Okay, you try and verify first. Yeah, you need to do like 9 computation basically. And then you should observe that you keep repeating. Yeah, you do first, you do first. I will tell you in general why is it true. Are you Benny? You Benny or not? You Nuri? No. And how about the other one? Oh, you're Benny. Oh, okay. I thought Benny is the guy. Benny and okay. Why only left two of you here? Yeah. Food poison. Yes. Okay. And then Hiba, you mean no? Oh, Hiba, you know. Okay. Okay. Are you happy or not? I'm still calculating. Still calculating? Still calculating? Remember how I got transpose here? If you don't take transpose, you won't get it. Make sure you see the transpose here. Okay, got it? Still calculate? Someone got it? Still calculating? 那算了嘛，Amber 有算嘛？啊，有啊，算到哪里了？Okay, all right. So what are you actually computing here? You see, can you see here? So if I name this column as V1, V2, V3, and I mean this is how I form this matrix, right? And transpose it means what? Columns will become row, row become columns. So I can also split this vector here become V1T, V2T, and V3T because column become row already. Okay, but how do you do matrix multiplication? Exactly, you are doing row time column. Okay, row time column. So what's the terms we are getting here? We are getting what? V1T times V1, V1T V2, V1T V3, V2T V1, V2T V2, V2T V3, and then V3T V1, V3T V2, and V3T V3. But what is this? What is the transpose time vector? This is what we define as a dot product. Okay, so actually we are doing v1 dot v1, v1 dot v2, v1 dot v3, v2 dot v1, v2 dot v2, v2 dot v3, and then v3 dot v1, v3 dot v2, and then v3 dot v3. So correct, right? The size, because the end product of a dot product is what? A number. So you have 3 by 3 matrix. But what did we show? This set is a orthogonal set. So meaning what? Off diagonal there are 0. Okay, so off diagonal there should be 0. But what are the diagonals then? These are the length of VI. But just now we show that this VI have length 1. So you get the identity matrix. Okay, so you don't need to go and compute every row times column, because we know from the theory, okay, the theory that we compute this one. Okay, UT compose, I mean this matrix transpose multiplied by itself is identity. So what I'm trying to say here is an m by n matrix has orthonormal columns if and only if you take it transpose multiplied by u is identity. Okay, so we have shown this theorem here. Although I show you the n by n cases, you can generalize to any size. Okay, so can you see here? This is like, okay, so if I can define a dot product of matrix, right? This is like the generalization of our generalization of what? Our v dot v equals to 1. Generalized to matrix. Okay. Okay. No? Yeah, generalized to matrix. So matrix says more than what v dot v equals to 1. V dot v equals to 1 just says that the vector has length 1. Okay, but if you generalize it to matrix, okay, it will say that your matrix has orthonormal column. Okay or not? Does it make sense? Okay. So because 1 is the, identity matrix is the identity in the matrix multiplication. 1 is the identity in the number multiplication. Okay, so it's like generalization. Okay, any questions so far for this two things here? Can get it? Okay, because how to show it? Basically, you just write the terms out. Okay, if they are orthonormal, the off diagonal terms are 0. Okay, and then only thing you need to care is about the diagonal. So what's the length? Okay, the question is what's the length? All right, and more nice thing about matrix with orthonormal columns here, you can see that if you have an X, you multiply with an orthonormal column, matrix with orthonormal column here, what you will get is the length of the new vector here is the same as the previous one. Meaning what? Meaning this matrix here will preserve length. Okay, it won't change your length. Okay, if your matrix, if your matrix has orthogonal columns and the column's length is 1, okay, you won't change the length of your vector. Second, ux dot uy equals to x dot y. Meaning what? You already preserve length, right? It also preserves dot product. Meaning what? Dot product have another information, right? Other than length, which is what? You have to remember all this formula. X dot y equals to the length of x times length of y cos theta. So it already preserved the length. It preserved inner product, meaning it also preserved the angle. Okay, so you also preserve the angle between two vectors. And ux dot uy equals 0 if and only if x dot y equals to 0. Why special? I mean, why we specifically mention about this? Because x dot y means what? They are orthogonal. Okay, so it also preserves orthogonality. Okay. I think we won't prove this. Maybe it's not hard to prove also. Okay, so matrix with autonomous column is really nice. You will preserve length, preserve angle, and preserve orthogonal. Okay, let's do this. I'll give you 3 minutes. Verify this. So basically, this chapter is about transposing matrix multiplication. And then length, finding angles from there. So combine these together. Okay, let's go through together here. Yeah, I think it's quite straightforward, the question. So let's try check. Okay, so you are given U, given X. So U is a 3 by 2 matrix, right? Okay. And then first we want to show that UTU equals to identity. Okay, let's do that. So UTU equals to identity. So what is UTU here? So UT, so we transpose U. So the columns become row become columns. Okay, and then multiply by U. How many things you need to check here? 2 times 3, 3 times 2. So you're going to get a 2 times 2 matrix here. So the first term you should get 1 over square root 2 plus 1 over square root 2. The other one you should get 2 over 3 times square root 2 minus 2 over 3 times square root 2. And then 2 over 3 minus 2 over 3 square root 2 minus 2 over 3 times square root 2. And then the last one, there are 3 terms here. 4 over 9 minus 4 over 9 plus over 3. Over 9. There's something wrong here. 4 over 9 over 3. Is there anything wrong here? Nothing wrong, right? Wait, something wrong here. So minus minus become plus. Okay. So what do you see here? So off diagonal term, they are cancelled. The diagonal term you get 2 over 2 over 9 over 9, which is 1. Okay. So we verify that this is identity matrix. And then second, you need to check that the length of ux equals to length of x. So can we check what is ux first? Let's check what is ux. So u apply to x, what do you get? Anyone tell me? Let's draw this. What did you get? Huh? Sorry? Anyone doing computation or not? Okay, what do you get? Edward. 3, -1, and 1. So first of all, you check size. Is the size correct or not? So u is 2 times 3. Okay, and then x is 2 times 1. So you get, hey, what am I doing? So u is 3 times 2. And then x is 2 times 1. So you get a 3 times 1, correct? Okay. So you get this. So what's the length of ux? Huh? What's the length of ux? Edward. Like Amber. Square root 11. Okay, so how do you compute it? How do you compute it? 3 square plus 1 square plus 1 square. Good. Okay, and then we need x, the length of x also, right? So the length of x is what? Square root 2 square plus 3 square and then take square root, which is also square root 11. Okay. But there are quicker way to show, you know. There's a quicker way. You can use theorem. Okay, how to use theorem here? How to use theorem? There's a quicker way to show the second statement here. Use theorem to show. How to use theorem to show? Huh? Want to try Edward? Because so this shows that UTU equals to identity shows that U has orthogonal, not just orthogonal, right? Orthonormal column. A matrix with orthogonal column will preserve length. Okay. Yeah, you don't need to compute also can. Just use theorem. Okay, so this show you how nice if you have a matrix transpose time a matrix equals to identity. Okay. Another thing I want you to appreciate is you see where is ux live in? Ux live in where? Which Rn? R3 but x R2 Okay, so actually you are comparing two vector in different space. One is R3, one is R2, but they have the same length. Okay, no. So okay, another word, U is a mapping from where to where. You take an R2, you take an R2 and then you map it to R3. Okay or not? So it's like you're taking this paper and then you see how this paper sit inside R3. Okay, R2 into R3. Okay or not? But their length didn't change. Didn't change, right? This paper didn't change in R3. Okay, just position change. Length didn't change. Okay. Right. And then next definition is we'll say that a square matrix is orthogonal matrix if it satisfies this property U equals to identity. So this one only work for square matrix. We didn't define it or for general matrix with orthonormal basis. Okay, we just define it for square matrix here. So U equals to identity means what? Actually, U equals to identity implies that the inverse of U actually is just U transpose. Very nice. Okay, it's very nice. You just transpose, you get your inverse. Correct or not? You spend 2 weeks learning how to find inverse, right? Correct or not? You do what? Elementary row operation, or you do the Cramer's rule. But if it's an orthogonal matrix, the transpose is automatically the inverse. Yeah, very easy to find. Right? No need to do so many row operation for finding cofactor. Okay. Okay, so far any question? So far any question? No? Okay. Anyone that I haven't taken your attendance yet? Anyone I miss out? Okay. If not, we continue with orthogonal projection. So just now we only project onto a line, right? So now we're gonna project into a space, a subspace in general. Yeah, so I think we have to recall what we had. So we want to reinterpret the theorem that we introduced last time. Let's bring this down. So we're gonna define new thing. So this theorem here. So now, so what's our motivation here? So previously we have this theorem, okay, and we're gonna interpret this theorem as orthogonal projection onto a subspace. Previously what we had was, so let me draw it here. So previously what we have is y, and then we just gonna project it on u. And so we do this projection here, we call this z. Okay? And then we call the other part scalar multiple of u, which we call the projection on u. On u on 2u of y at that time. But now, what we're going to do is we have a space spanned by potentially more than one u. Okay, maybe there are 2u here. And then we have y again. So how about make this y into a blue line here? And what we're going to do is we project this y onto the plane. Okay, onto the plane spanned by this u1 and u2. Okay, so how are we going to define this? Do we have notation for it? So yeah, we have notation for it. So this projection here, we will call it a projection onto the subspace spanned by u1, u2 of y. Okay, so how do we do this? How do we define this? Okay, we define this. So, well, so how do we define this? What do you think? How do we define this? So one hint is very similar to what we have in this theorem here. Yeah, let you think about first. Let's not tell you the answer first. Let you think about how to do this, how to define this approach. Okay, maybe I give you a hint. Okay, I give you a hint. So previously, how we defined this approach? We simply take y and then dot it with u and then divided by the length of u squared times u. But now you got u1, u2. What can you do? What can you try to do? You can do it on one, right? I mean, if you learn computer here, right? You guys should know about induction, right? Induction. Do you guys know induction? You know what's induction? Induction. Okay, how about loop? You guys know loop? What's loop? 循环. I mean, what's a loop in your coding? What does a for loop do? Repeat, right? You repeat the same process, right? Okay. Can you repeat the same process for this two factor or not? Okay, let's say we repeat it. Okay, let's say that we just try. We just try. So take y dot u1 over u1 dot u1 plus time u1. And then the other term is u dot u2 plus u2 dot u2 u2. Okay, potentially we can form this two vector here. Okay, we can form this two vector. But where does this two vector live? Let's play around first. So where does this two vector live? They are just scalar multiple of u1 and u2, right? So it should stay on the same line as u1 and u2. Okay, so maybe it stay on this line. How about use different color? So here and here. Okay, but in this picture here, right? It doesn't quite do what we want, right? We want a vector that is somehow live in the sum of these two vectors. Okay, so potentially maybe we can try and add them up first. Okay, but what else you want this projection to do? What else you want this projection to satisfy? So now you need to ask the question, what are we doing here? What are we actually wanted to do here? We want to split this y into what? Two orthogonal, sum of two orthogonal vector. Okay, so let's call the orthogonal guy z again. Also call it z. And then we want to split y into what? The projection part and the z part. The projection part and the z part. Okay, the projection part and z part. Okay. So what's this extra condition here? You need to check whether this z is orthogonal to this proj or not. Okay, so let's say we say that, oh, we want to define the projection as this sum here. Okay, so we know the projection already. We also know y, right? So in principle, we should know how to find z. Again, not same. You just take the difference. So the question now becomes, if I take my z, so let's say y minus proch y. Okay, so before that, so my z dot with my projection should be 0. Correct or not? Okay, we want this to be 0. So now can you check that whether y minus proch y dot with proch y is 0 or not? Is it 0? Yes 啊，有冇明啊？哪一位同学？哪位同学？你叫什么？超 OK， 昌瑞哦，李昌瑞对，李昌瑞。Is it 0? You think is it 0 or not? You think it's 0? Why? How do you see that? Y minus projection of y is z, and then y. No, okay, right. So no, I had the question, sorry. So let's repeat the question. We actually want to verify this. We want to verify. So this z, so the logic is I define proch first, okay? And then I find z. I'm gonna verify this 90 degree. Is it true or not? Does it make sense? The logic, where's the logic here? First, I define the proch first. Okay. Second, I find the z. Third, I want to show you that this 2 has dot inner product 0. Can you follow the logic? 懂我在讲什么吗？不懂不用紧，但是要问，懂我在讲什么？ Does it make sense? I first come up with this proch definition first, okay? And then I try and find the z, right? I can find, right? Because I just take the difference, y minus this proch. Now, my question is, do we really get this z as a 90 degree, as orthogonal to my proch or not? I need to verify that. Okay, so I need to compute this y minus proch y. But how to verify? Just compute. You need to compute it. Okay, but if you compute it, what do you get? Y dot proch y minus proch y dot proch y. I don't have calculation in my lecture notes, so let's see if we can get it out. This. Okay. What do you think? What do you think? I mean, we need to compute, correct or not? Just compute it. Okay, just compute it. So y dot proch y is what? So y dot proch y we have. Plus proch y dot proch y. So we take 2 proch y dot together. Okay. So dot product, not multiplier. There's some. So here's the dot product. Okay. First question, do you get headache or not if you see so many dot products? Do you get headache? Please get used to it. It's very normal here. Okay. So although there's a lot of dot product, but how should you view dot product as? Nuri, how should you view a dot product? What does dot product give you if you dot two vector together? No, a number. It is a vector, but it's a vector as a number. Number is also a vector, but it's a number in particular. So meaning what? There are a lot of number here. So these are just this quotient in particular are just number, which is a scalar. Just scalar. Okay, it's just scalar. Okay. Right. So if you want to dot y with a sum of a vector, how do you dot it? You just take y dot with u1. Right. And so here is a scalar. And then you take your scalar out. And then you take y dot with your vector. Okay. Oh, here is not plus, oh, here is minus. And how about the other one? How about the rest? How about this one? How many dot product you're gonna get if you expand this? How many? Okay, let's make it simple a little bit. So here you can view it as alpha 1 u1 plus alpha 2 u2 dot with alpha 1 u1 plus alpha 2 u2. So what you're gonna get? Alpha 1 square u1 dot u1 and then plus what's the other term? Alpha 1 and alpha 2 u1 dot u2. Okay. And then alpha 2 alpha 1 u2 dot u1 plus alpha 2 square u2 dot u2. Okay. So there are so many terms here. Okay, not very friendly. But let's say, if we have extra condition here that kill these off diagonal term. Okay, let's say u1, u2 are orthogonal. Okay? If they're orthogonal, what happened? It goes to 0. Then what's left over here? What's left over here? We were left with, let's say, so suppose, so here, let's suppose a new thing here. So suppose u1 dot u2 is 0. Okay, then we can make this calculation easy. So what happened to this calculation here? So what's left is y dot u1 over u1 dot u1 squared, because the scalar will get square, right? And then you will get u1 dot u1 minus second term u1 dot y1 y dot u2 u2 dot u2 squared times u2 dot. Okay. So what did you see here? So what you see here was, if I'm gonna multiply the square root, the square into your fraction, again, you can see that the length of u1 and u2 square will cancel by 1. And then the whole term will cancel. Okay. Can you see? Can you see or not? Cannot see? Okay. Maybe a bit big. Yeah. So let's do it one by one. Yeah, let's do it one by one. So let's continue. Maybe you are not used to seeing so many dot products, so let's do it one by one. So how about first one? First one, did you see that these two scalar is the same? It's the same, right? So we group them together. Y dot U1 square over U1 dot U1. How about the second term? Also, you have two same scalar here. Also group them together. Okay. But how about this two here? How about this two here? How about this two here? Okay. If I expand the powered out, what did you see? Y dot U1 square over U1 dot U1 square. But you are multiplying by a U1 dot U1. So they will cancel. Okay, similar for the next term. Sorry, here is minus. Y1 dot U2 square over U2 dot U2. Okay, so you can see that. Can you see or not? The four terms here cancel. Then you will see that the Z is orthogonal to your projection. But with a condition. What's the condition? What's the condition? You need to kill the cross term here. But killing the cross term here means what? You need to make sure that you start with U1, U2 that's orthogonal. Okay. So the theorem is, so what's this theorem here? If you have a subspace, okay, with an orthogonal basis, then we can write your y in terms of y1 plus y2 such that y1 is this projection. So it's the projection that we define. Proj on this subspace here of y, okay, defined as the sum, okay, sum of linear combination of u1, u2 up to up such that how do you find the coefficient? It's exactly the same way to find when you want to project to a line. Okay, so you project to every basis first, basis element, and then you add them up. Okay, does it make sense? Okay, I do the two-dimensional case for you. So three-dimensional, four-dimensional, n-dimensional is the same. Right, you can try and expand it. Use the way I show you. Okay, it's the same. So this is the general way to project. Any question now? So how to remember this formula here? How to remember this formula? How to remember? You should start with the easiest case, the line one. Okay, the line one, just U1. Okay, it's y dot U1 over U1 dot U1. But if you have to project on a subspace that's dimension more than n, what do you need to do? You need to start with an orthogonal basis first. And then do the same projection onto each basis. And then add them up. Okay, that's all. Can remember or not? The process. Okay, it's just doing projection onto multiple lines. Okay, multiple lines that are orthogonal to each other. Okay, onto multiple lines that are orthogonal to each other. A question? No? Okay, let's try one example. Okay, I'll let you try first. Give you 3 minutes. See if you get the right answer or not. So we will check the final answer first later. Okay, let you compute. I don't know how you compute, but later we check the final answer. And then we discuss that. Okay, let's see. So we have U1. Okay, maybe we are still in R3, so actually we can draw this 3 vector here. Okay, so 2, 5, -1 is in the last acton. Okay, so we split. Basically, we split our R3 into 8 parts. So octon. So split into October. So we have this U here. And then where's the U1? Also U1 here. U2, -2, -1, 1. So where is it? So it's in the second octon here. It's U2. How about Y? Where's Y? So Y is in the first octon. So let's use the other color. So maybe around here. Okay, so we want to ask what's the orthogonal projection of Y onto this plane. Okay, onto this plane here. So maybe this one need to go a little bit up. That. Okay. Right. So Y2 is orthogonal to W. Another notation, we will write it as Y2 is in W perp. So remember how we define this W perp here is everything that is orthogonal to W. Okay, so this perp is representing the 90-degree. Any question? Okay. Okay, so this is just a notation. Right. So anyone get solution or not? So what is Y1 here? What is Y1? Anyone? What do you get? I want to try a solution. Y1, Y2 here. 所以有算约定有算吗？约定还没有算完，谁算完了？Anyone finish? -2, 2/5, and then 2, and then 4/5, like this. Y1. Okay. Y2, 4/5, and then 0, and then 9/5. Okay, let me see. Correct. Huh? Which one? Last one is 11/5. Anyone got different answer or not? Same. You also get the same? You get the same? Then my solution is wrong. Let me see. Sorry? Last one should be 1/5. Can we verify it? So let's verify it. So what's the formula for Y1 here? So Y1 here is a projection, right, that we defined just now on W. So what's the term we have to have here? So Y dot U1 over U1 dot U1 is U1 plus Y dot U2 over U2 dot U2 times U2. Okay. Anyone tell me what's the scalar you get for U1? What's the scalar you get? Now, but 30. Okay. So let's check one by one. We slowly check into the details. Okay. Slowly check into the details. How about scalar for Y2? 3/6. Okay. Yuan Yuan, you got this two scalar or not? This two scalar you get the same. Then should be the next step. 你抄错题。OK。OK。你 U1 抄错，但是你的 scalar 是一模一样啊，这么厉害 ？OK。So basically copy the wrong U1, but scalar turns out to be the same. Okay, so if you combine this, you should get -2/5, 2, and 1/5. Okay, so this one you should also change to 14/5. Okay, can follow? And so how do you get Y2? just to confirm, you take your y minus your y1. Okay, take your y and minus your y1. Yeah, so what's the checking you can do here? What kind of checking you can do here? We need to make sure that this vector, this y2 here is orthogonal to w. So there's one checking you can do here. So take your y2 and then dot with your u1. It should be equals to 0. Similarly, when you dot it with u2. Okay, so this is the checking you can do. Okay, you get the right projection. Any question or question? All right. No, if no question, let's continue. Then next theorem is if y is a vector already. Okay, so if you are already inside this span of w, what do you imagine? What do you imagine here? What's the approach of y? It should be just y itself. Correct or not? It should be just y itself. Okay. Is it obvious that this theorem? Is it obvious? Obvious or not? Is if your y already lie inside your w, right? The projection should be itself. Okay, so this link back to your previous theorem here. Okay, so if your subspace is spanned by u1 to up, then for every y in w, you just write it as a linear combination of u1 to up by this scalar. And then this scalar is the same scalar we use in the projection. Okay, so if it already live inside your subspace, then the whole thing is just approach. So previously, this is just approach of w of yx. Okay, it's the same formula. It's the same formula. Also makes sense, right? Nothing to project already inside it. Okay, so this theorem actually is checking whether the approach y that we define makes sense or not. Okay, it makes sense. Already inside there is the same. It's the same guy. Okay, so if I want to put a remark here, so let's remark here. So this theorem says that the orthogonal, the definition of orthogonal projection makes sense. Okay, makes sense. If you project to something else, then don't you think feel weird? Again, must project to the same because you are already inside. You shouldn't go to other places. Okay, next, the approximation theorem here. The best approximation theorem says what? If W is a subspace of Rn, and then let Ry be any vector in Rn. If y hat is approach y, and then v is not equals to y hat, then the length of y minus y hat is less than y minus v. What does this mean? Can you imagine this picture or not? You imagine this picture? So let's bring this down. Let's talk about this idea here. Can you imagine or not? Imagine this picture or not? Okay, let's draw this picture here. Okay, right. Let's draw this picture. Okay, so you have a W. So let's draw this W first. Let's draw this W. And then Y is any vector in Rn. So any vector, let's say here we take R3. Okay. R3. And then W is two-dimensional space here. And then where's y hat? Where should y hat live? Where's the projection of y live? It should be a vector on the plane. Okay, it should be a vector on the plane. Such that what? So there's the definition of y hat here. Such that if you take y minus y hat, you should get the orthogonal vector here. Right or not? Okay. And then it says that if V is another vector in W, if V is another vector in W, so let's take another one. Maybe this one. Okay. What does it say? It compares two quantities here. What are the two quantities here? One is y minus y hat. So y minus y hat is this part. Should we use that color? This part here. Okay, y minus y hat. Y minus v, you should form a line from this v here, let's call it v, to y. Okay, so here is y minus v. Okay. So any other this line should be greater than this vertical line here. Make sense or not? Make sense or not? Go and you got a pen, right? Got a pen or not? Put on this table. Okay. And then maybe slanter a bit. Okay, maybe I need the other pen. Okay, you slanter a bit. Right. So you slanter a bit, right? And then you look at the vertical distance here. And then you compare with all the other distance. Should be shorter. Okay, so this is what this theorem tells you. But obviously it requires proof. I think we won't prove it. I will show you the proof inside the notes. But I mean, intuitively or by looking at this pencil example, you should see that the vertical one is the least distance. Okay. Yeah. Because if you deviate from any of this orthogonal line, right, your distance should be longer already. Does it make sense? All right, huh? Okay. Yeah, agree. Okay, good. If you don't agree, take two pens, play around with it. Okay, and then I think we won't go through the technical details, but at least you need to know the concept. Okay, so let's look at this examples here. So we have U1, U2. Okay, if you can, I mean, it's a good practice for you to draw it. Okay, because you need to understand what people say, right? So better you have a picture in your mind. Okay, better you have a picture in your mind. It's very important. The picture in your mind. When you listen to what people say, right? The picture in your mind is very important. Because sometimes when you get argument with others, right? Actually, what you say, right? You recall the bad memory of that guy. So when the person want to argue with you, right? They actually argue from their bad memory. It's not from your point. You get what I said? You understand what I said 吗？听不懂啊？有跟人家吵架过？有没有跟人家争执过？没有没，那么好，没有啊。通常我们在争执的时候他其实不是在跟你吵了，他是过不去他自己的坎，你明白吗？So you need to like how to say guide them. Okay, you need to guide them to the picture that you want to discuss. Otherwise, they just discuss from their bad memories. It's very hard. Okay, cannot discuss one in that case because they are very sad. Okay, yeah. Okay, so mathematics is very clear. Okay, let U be this, U2 be this. So there's only one thing you can think about. Okay, just draw it on R3. So 2, 5, -1 is where is it? Did we draw similar thing before? Is it the same vector we play around? So 2, 5, -1 is here, U1, and -2, 1, 1 is in the second quadrant, like that. Is it the same one we drew before? Yeah, it's the same one. Okay, but y changes now. So y becomes somewhere else. 9, -1, and then 4. So somewhere here. Okay, good. So we're gonna look at the closest point in W. So here, let's form a plane first. Closest point in W. Closest to who? Closest to Y. Okay, so you know what's this question asking? Find the point in W that's closest to Y. So what's this question asking? What do you think? Closest point in W. So you need to find point in W, right? And then form a line between Y and this point in W. So how to find the closest one? Based on what we have discussed. You need to project orthogonally. Okay, you do need to find a orthogonal projection. Okay, so by part A, sorry, by previous theorem, well, by the best estimate approximation theorem, okay, the point in W that is closest to Y is the projection of Y. Okay, it's the projection of Y. Okay, because if you move away from the orthogonal projection, your distance will become longer. Okay, so how to find projection of Y? So you take Y dot U1 over U1 dot U1. So repeat the formula times U1 plus Y dot U2 over U2 dot U2. So basically, this question again asks you to find the orthogonal projection. Okay, again asks you to find the orthogonal projection. Well, I think we haven't computed this, right? So if you quickly compute this, you should get -2/5. Okay, one question. Are you bothered with the question asking about point, but you give a vector solution here? Are you bothered by this? Some of you are bothered. Edward said no. Edward, why? Sorry? Huh? Why? 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 Point and vector the same? Yeah? How are they the same? Mm-hmm. Okay, very good. So in this case here, what did you see? So if you try to relate this y, right? Why is it so blurred? So if you relate this y to the orthogonal projection here, so let's draw the orthogonal projection. Okay. And then what's this point here? This point is a vector from the origin, actually. Okay, it's a vector from the origin. Okay. But y is also a vector from the origin. So surely it will project to a vector that's coming up from the origin. Okay. And then this point is described by this vector here. So, well, I mean, if you really want to differentiate, right? Actually, we can, how to say, wait, let me move this down. Like last time I explained to you, right? You can write it in this point form here. Okay, since the projection of y is this. Okay, so if you are really bothered, we can write it as a point form, but they are the same thing. Okay, points and a vector starting from origin is the same. Okay, yeah. But I think in this course, I think we won't differentiate so much between these two things. As long as you give one of them is fine. Okay, as long as honestly speaking, you know that asking the point in the subspace that's closest to y is to find orthogonal projection, then you are good. Okay. 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 Right, next. Then the question asks you, What's the distance then from y to w? This question got problem, I think, got bug here. This question got a bug, you know. You know where's the bug? Why w got a bug? W is so big. Yeah, this is about, yeah, so this is about w is so big. W itself, there's no bug, you know. W already defines a span of something, linear combination. But the point is, there's so many points in W, out of which point you want to choose. Okay, actually, we should define this, right? Yeah, this question is not well written here. Okay, so maybe we should define it. Let's define it. Yeah, so how do we define it? So let's make a definition here. So I mean, maybe you can guess already. So maybe you can guess what we want to do here. You want to guess? How should we define the distance from y to a subspace? Want to guess? You take the length of y minus approach of y onto w. Okay, so we define this. We take the shortest distance. Okay. Otherwise, how to take? Which one we want to pick? Because if you pick another point, right, the distance will just get larger and larger and larger. If we take the supremum, what happens? If we take the largest one, it's infinity. So there's no point to discuss distance in that case. So instead, we take the smallest one. Okay, we take the smallest one. Okay, so in this question here, what it wants us to do is just to find what's the length of y minus approach y. Okay, so basically this is 1, 2, 3 minus negative 205. 1. Okay, so this is the length. And if you go through this, it's 7 over square root 5. Okay. Okay, I think this question is pretty standard, and we will use it as a quiz and final exam question. Okay. I mean, one of the type of question that can come up. Okay, so far, okay or not? Right, continue. Yeah, so let's say we make our life easier. U1 until UP is orthonormal, meaning their length is 1. Then we can remove the denominator. Okay, we can remove all the denominator because if we make our orthogonal set as length 1, a unit vector, for example, then we can remove all the denominator. And there's a nice description about this. We can rewrite this formula, right? This linear combination as matrix multiplication. Okay, the other way around. Instead of UTU, we use UUT. Okay, we commute. Okay, this guy will give you the linear combination that we had for our approach. Cannot. We cannot use UTU, right? You know what happened if we use UTU? It will just be a identity matrix. Okay, instead, UUT will do the job. Okay, UUT will define this linear combination. Do you believe or not? You want to verify this? You want to verify this? Okay, so let's verify this. So let's verify this quickly. So U is what? Yeah, U is basically just putting all this UI together. Right, it's what we did just now. But UT, we flip the column become row. Okay, we flip the column become row. So I get U transpose in the horizontal way, here vertical way, right? Or U2 horizontally, and then UP horizontally. And then multiply by this Y here. But how matrix multiply a vector? Row time columns, right? Okay, row time columns. Okay, row time columns. Meaning what? Okay, so you take row time columns. Okay, row time columns. In a the dot product. And I said that, yeah, it's actually U1 times U1t times Y, U2t times Y, and then UP E times Y. Row times column. Okay, maybe let's remember the size also. Okay, let's remember the size. So let's remember the size. Size. Okay, so what's the size here? Ui are in subspace of Rn. So these are Rn. Okay, so what are the size here? So here are m times 1 size. All of them are n times 1. Okay, so all together you should have n times p, correct? Or your u is like n times p size. Okay, so if you transpose it, what happened? You got p times n size. Okay. How about your y? Leh? Where did you pick your y? Where do we consider our y from? Actually, will our y also come from Rn? Is it Rn? Yes, Rn. Okay, so y is a n times 1 size. Okay, so if you're gonna multiply a p times n times 1, right? What do you get? Huh? P times 1, correct. Okay, you get a p times 1, correct. Okay, so what do you expect here? All these actually are just numbers. But remember, what is a vector t times a vector? This is a definition of an inner product. Okay, so basically what you had here was bunch of inner product. Hey, do you think that this inner products look very familiar? Familiar or not? Is it familiar? Why dotting with all the UIs? What's this? This is the scalar that we had, right? Yeah, this is a scalar we had. Okay. And then what? Hey, recall back 2 weeks ago. How do we define this? Matrix vector. Matrix vector multiplication. This is just a single vector. Oh, this is a p times 1 size. Oh, this is a single vector. Can you go back to the first time we defined matrix vector? What are these vectors doing? These vectors are the scalar for your column vector. Okay, so what do you get here? U1 dot y times U1. And then you take their linear combination. This is the very first time we see the matrix vector multiplication. Okay. But maybe you ask the question of, hey, sir, the dot product order different, eh? Does it matter? Matter or not? X dot y is it equals to y dot x? Yes or no? Dot product commute or not? Dot product also commute, eh? X dot y equals to y dot x. Correct or not? Because x1 times y1 equals to y1 times x1. And then you just add them up. Yeah, so these two define the same thing. So if you want to ask u equals to identity, what's the use of ut? You can find your projection, orthogonal projection. You can use UUT to find your orthogonal projection. Okay. So instead of going through this going through this kind of nightmare, right? Where's the nightmare? Where's the nightmare? So we had this nightmare last week, right? I mean, going through this kind of nightmare, all the dot product. Instead, what do? You just take UUT, do the matrix multiplication. Okay, you will get the same answer. Okay, no need to write out so many dot product. Okay. Okay, but the first thing is you need to make sure that your U is is formed by orthonormal column. Okay, that's the only thing you need to check. Right? That's the only thing you need to check here. So your U here should be made out of orthonormal basis. Okay. So if this subspace is just Rn itself, that's mean what? This U is actually a orthogonal matrix. Okay. Yeah. Okay, let's do one more thing before we break. Maybe we introduce it now and then in the next lecture we do it again. Okay, I want to reinforce your memory because this thing is very not that intuitive. I mean, it's intuitive, but a bit tedious. Okay, let me show you what is going on here. Okay, let's learn one more thing before we break. And then on Wednesday, we will repeat this thing again. Right. So we start with W, span of two things. Wait, before reading all these, this first part already makes sense, you know. So what's the picture need to appear inside your mind here? And what's the picture? You got 1x1, you got 1x2, and then you look at the span. Okay, so this is the picture you need to put into your mind first. Second, fill in the blank, filling what is x1 and x2. So actually these two are vector in R3. Okay. First question you can ask, correct or not? If these two are linearly dependent, what happened? This span become a line. Correct or not? Span of one thing. So are they linearly dependent or not? There's one place you can easily check already. If two of them are linearly dependent, right, they should be scalar of each other. But you see, this one got 0 here. How can you create the 2 here? Cannot. Okay, if you're gonna create this 0, you only can multiply 0. But this is not a 0 vector. Okay, so they are not linearly dependent, so they must span non-trivial subspace with 2 dimensions. Now we're gonna construct an orthogonal basis of V1 and V2. Okay, so well, these two are perfectly good bases, no? Because they are linearly independent. Okay, and then they're span. They are bases already. The problem here is these two are orthogonal or not? Why? Why is it not Yuan? Okay, not that. What's their dot product? So x1 dot x2 is what? What do you get with their dot product? What do you get? 3 plus 12, which is 15, which is not 0. Okay, so they are not orthogonal to each other. But can you make a orthogonal basis or not? What do you think? Based on what we learned. How? Edward? Based on what we learned, can you find an orthogonal basis or not? We already close to orthogonal basis, right? We already have basis, just that they are not orthogonal to each other, not 90 degree. So can you make a 90 degree one out of these two non-90 degree one? Can or not? What do you think? Based on what you learned just now. Remember? Orthogonal projection, how? How do we use orthogonal projection? Can you tell us how to use orthogonal projection? What can we do here? We got two vectors, same setting or like orthogonal projection. Then what can we do? Okay, so meaning you want to project your x2 to x1, right? Okay, so you project your x2 to x1, and then you will find the orthogonal part, which is x2 minus approach x1, x2. So now, where is your orthogonal basis? Where's your orthogonal basis? Now, where is your orthogonal basis here? Where is the, let's say, what's the V1, V2 you can take here? You already do orthogonal projection, right? So what are the V1, V2 you can pick here? Where's the orthogonality here? First of all, who orthogonal to who? X1 and x2 minus approach s2. So meaning I can take v1 as my x1 and v2 as my x2 minus approach x2. Okay. Okay, no. Well, I mean, if you want to take v1 as approach x2 also can, but no need. Or not, they are just scalar to each other. Okay. This is not the only way, right? This is not the only way. Correct or not? You can also project your x1 to x2. Okay. And then find the orthogonal part. Yeah. Okay, so there are actually few ways to do it. Okay, so let's do this and then we will finish here. Right. So the first step is if we follow Amber's logic, so we let our v1 to be x1. Okay, so we fix the direction first. And then how to find v2? So v2 is just x2 minus approach of x1, sorry, approach of x2 onto x1. Okay, not x1 correctly, correct or not? So to be precise, we want to project onto the span of x1. Okay, I mean to be consistent with the notation of orthogonal projection to subspace. So let's make it consistent. But in the exam, if you write U1, I also understand what you are doing. I mean x1. Okay. Okay, so what do we compute here? So here, x2 is 1, 2, 2. So projection of span of x1 is what? So you take your x2 dot with your x1 divided by the length square. So it's 360 dot with 360 times x2. Yeah. Okay. Yeah. Okay. So I think you should get 002, if not wrong. And maybe you can verify this before we finish. Yeah. Anyone verify this calculation? Try and verify this before we finish. Where did you get this calculation? Haven't. Okay. No. You sorry, you don't want to answer. Okay. Yeah. Anyone got the answer? Bryson, what do you get? Huh? 002, same. Okay, good. Okay, so what do we have here? So we'll say that then V1, V2 is an orthogonal set of non-zero vector in W. Okay, and we know that orthogonality implies linearly independent by previous theorem. It is linearly independent. We also know that the dimension of W is 2. Do we know this? Do we know this or not? Actually, in principle, we have to check like what we said. So okay, let me write down what I say. As dimension of W is equal to 2. So let's make a bracket here. Since we check that x1 and x2, okay, let's put here, are linearly independent. Well, if you question this, right, do you know how to check this or not? Two vector are linearly independent. Do you know how to check? How to check? Sorry? 90-degree, yes, sure. But in this case here, we don't have 90-degree, right? So how to check? Yes, you need to do the row reduction. Make sure that every column have a pivot. So this one is a row reducing the matrix formed by x1 and x2. So you need to go back to the original method. Because we don't have orthogonality here. Remember, orthogonality implies linearly independent, but not the other way around. Okay, not the other way around. Because I already draw you the picture before. So as we know, the dimension is 2. So we have 2 linearly independent vector now. So what? So the set V1, V2 form a basis for W. Okay. Okay. Any question? 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 Sorry. Okay. Yes. Sorry. V2 is wrong. What do you mean that V2 is wrong? Calculation is wrong. You mean this part? This part. So what do you think? You mean here got 2/3? What do you mean? What's the? You sure? 2/3 and 3. Yeah, let me see. Project. Here, you mean here, right? Here, this one. Okay, thank you. Yeah, sorry. Here should be 360. Well, I mean, one way to check, right? So one way to check is if you get this solution, right? Go and dot with your x1. So if you take, so let's check this. So if you're gonna do a check here, so what you're gonna do here is I take 0, 0, 2 dot with my x1. Do I get 0 or not? Correct? I should get 0. Okay, there's a lot of checking you can do in this course. One nice thing about this course is you can attack one question from various ways. So if various way agree, there's a very high chance you get the right answer. Okay. So in particular, for example, the reason quiz, the quiz Quiz 3. There are a lot of ways attack the same question one. Actually, there's one very convenient way. Actually, the first question can solve all the question. But a lot of you, like, for every question, you start all over again from the definition. It's fine, it's fine. But if you know that the calculation in the part 1 can apply to all, then it will save you a lot of time. Okay, so actually in last quiz, some of you finished quiz quite early, but still have a number of you still calculating. Get what I mean or not? Because you restart your work for each question. Actually, you can read the first question in different way to get this answer for the second part. Yeah, we will discuss this on Wednesday. Okay. Yeah. Okay. Okay, we have discussed for 2-dimensional, right? How about 3-dimensional, 4-dimensional, 5-dimensional? What do you think? What's the process? So let's draw some picture for you to think about. Let's say you have 3, right? 3 vector, they are not 90 degree to each other. So how do you create 3 vector that are 90 degree to each other? What do you think? So let's say here U1, U2. What do you think? I want to try. Who want to try? Ming want to try or not? Don't want to try. Try lah. Here can make mistake one. Hey, if you go to workspace, right, you cannot make mistake. Did I tell you a story? Did I tell you before? I tell you before. What did I tell you, Edward? Huh? Something about what? If you go to workspace, if you make mistake, you know what happens or not? You know what happened? Either worst case, your boss fire you. The worst case. The boss fire you. The other case, you cannot say things inside your workplace, you know. There's no one believing in you. You understand what I say? 懂我在讲什么? You understand what I say? If you make mistake inside your workspace, no one want to listen to you. No one listen to you means what? Means what? Never mind lah. No one listen to me. Never mind lah. 是吗？是这样吗？ Never mind lah. It's very hard for you to survive inside the company, you know. It's very hard. So that's why people will jump here, jump here, jump there, jump here. One of the reason is this. Okay, you cannot have a very good relationship with your colleague. Okay. Actually, this happens quite frequently in your school, this school, university here. The turnover rate in this university is very high, actually. So the lecturer comes here and go, come here and go, come here and go, come here and go. I think you also experience it in your program. Did you experience it? Did you experience or not? Or you haven't stayed long enough? Your lecturer go, very good lecturer, but go, don't stay here anymore. Okay, you should think about this. And work culture here. Okay, so why I say about this? Oh yeah, so what I want to say here is make mistake inside class. Okay, inside here, when you are learning, make mistake. Okay, if you go out and make mistake, no one will forgive you. Okay, so here, I still can forgive you. We don't have exam marker now we're just discussing. Okay, so how to do? Who want to try? Want to try? Jiaming want to try or not, Jiaming? No one. Anyone want to try? If no one try, then we cannot finish. Okay. So you want to project who to who? Where is x1 here? No x3, right? Okay. So you want to project u3 to u1. Okay, let's do that. So if we project this, so maybe we'll get something like this. And then we'll get 2 parts, right? One is the projection part. Okay, let's write it larger. make it into the projection part. Open it up. So what have you done here? So what have you done here? So let's make it a bit systematic here. So we're gonna produce a set of. So let's put the question here. Produce set, an orthogonal set. Okay, an orthogonal. V1, V2, and V3. Let's call it a new name. Okay, to differentiate from the old one. So seems like what you have done is what we did before, right? You get your V1 out to be what? U1, and then you found another orthogonal vector here, which is U3 minus projection of U3 onto U, or the subspace spanned by U. Okay, so the problem here is how to find V3. What do you think? How do you find the third orthogonal vector? But what does this third orthogonal vector have to satisfy? It must be orthogonal to the previous two. How to create another orthogonal vector that's orthogonal to both V1 and V2 that we created? Huh? I'll try something else. So you look at the span of U3 and U1. Look at the span of these two. Yeah, let me draw it. So U3 and U1 is here. And then what do you want to do with it? You want to project U2 to the span of U1 and U3. Okay. Sure, this will confirm that U2 is orthogonal to U3 and U1. But we want it to orthogonal to V1 and V2 instead. Okay, so let's write down what Zheng Yang trying to say here. So how about consider the projection of U2 onto the span of U1 and U3. Sure, we can consider this. But the question is, does this orthogonal to V1 and V2 or not? Okay. We know that this will orthogonal to U1 and U3. Right or not? Okay. But does it orthogonal to the new V1, V2 we pick? Okay. Not sure. It depends. Correct or not? Because surely it is orthogonal to V1 because V1 equals to U1. But how about V2? V2 we changed already. It's not just U3 anymore. It's U3 plus something else. Okay, which is this blue line here. Okay. Instead, we should project our U2 to V1 and V2. Okay, so we should project our U1 to the span of V1 and V2. So can I draw this? Let's see how I draw this. Okay, so we should project. I think it's a good idea to draw it. Okay. You know where is the span of V1 and V2? So let's write out properly first. So V2 is here. Okay, and then here is V1. Okay, so it's a span lines. Okay, and then you want to project your U2 onto the plane. So I think where's the 90-degree here? Maybe the 90-degree should happen here. Okay. Yeah. So you should take your U2, take away the projection of U2 on the span of V1 and okay. So to answer Zheng Yao question just now, right? Can we take U1 and U2 or not? U3 or not? So the question is the span of U1 and U3 the same as the span of V1 and V2? Okay, if they are the same, then you can. If they are not, then they might produce a different thing. Okay. Seems like in this picture, they are the same plane. But I think we need to check. We have to be safe. But does it make sense for V1 and V2? Yeah, because you want to do a projection that's orthogonal to both V1 and V2. Okay. Got question? Any question? Maybe next time we come back to this method again for general. Any question before we break? So this is the third dimension. So fourth dimension, fifth dimension is the similar. Huh? Before we finish. Any question before we finish? Yes.
Span V1, V2 is basically the sum of
Linear combination of V1 and V2. What do you mean by the sum? This plus this. What do you mean?
V
Ah.
vector of V1 projection plus the projection of V2.
So span of V1, V2 is all thing looks like this.
I mean the projects.
Oh, yeah, sure. So wait. Yeah, sure. So how do you think of this? So let's call it W. So if these two vectors, right, you can think it as a plane, and then we project the U2 into this plane here. Like this. Is this what you want? This what you want? What's your question?
Span V1, V2 is not formula.
Sorry?
That is the project span V1, V2 and U2. How to do this projection? Two projection.
Okay, yeah, correct. Oh, okay. Oh, yeah, sure. So, okay, I think I get what you mean. Okay, so, okay, right. So you're asking about the definition of this. Okay, so you're asking about the definition of this. Correct? The definition of this. So, what's this definition? This is the generalization of a project onto one line, right? So what do? Basically, you take your U2 dot with your first vector and then divide by the V1 length times V1 plus U dot V2 again divided by the length square, so the product, and then multiply by V2. So you just take the sum of how you project on each line. Yeah. Yes. Okay. Yes. Yeah, this is pretty important. How to go from orthogonal projection onto a line to a space. Yeah. If you have a space, you should know that it's span of different line, and then you just do projection on each line and then sum them up. Okay. Yeah, we will come back to this Gram-Schmidt process again. This is what we call a Gram-Schmidt process, creating an orthogonal basis. Okay, we'll see you on Wednesday. Hey.
就是他说的那个 U1 和 U3的
Yes.
那个。
啊